Okay, so I think we'll get started. So welcome to this final session of this Advances in Verification workshop. I'm Deepak D'Souza. I work at ISC in Bangalore, and I'll be the chair of the session. So it's a pleasure to have Jaco van der Paul as a speaker for this session. So Jaco is at Aarhus University, and he also has a joint position with the University of Twente in the Netherlands. And Jaco basically works on verification, control, testing of safety critical and embedded systems using techniques like model checking, theorem proving, etc. And today, Jaco is going to be telling us about how to make model checking efficient by parallelizing and using smart algorithms and data structures. So welcome, Jaco, and over to you.
Thank you. Thank you for the introduction, and thank you to the organizers for the invitation. So yeah, I will guide you through some of our research of the last 10 years. It's joint research with a couple of PhD students. I've mentioned the 3 ones here that contribute most to the contents I'm presenting today. Actually, I also gave a similar presentation at Conquer end of last year. So indeed, the main theme is to make the model checking algorithms parallel in order to speed them up. I will spend most time on explicit state model checking, but in the end, I will also come to a parallel version of symbolic model checking. Okay, so yeah, let's first look into the motivation. So model checking, as you all know, requires to explore a quite large graph because the state space explosion is still with us. These graphs are not typically not the input to the problem. The input is often a quite concise model or a program. But then from this program or from this model, we generate this large graph on which we do the model checking. Now, there are a lot of approaches to combat state space explosion, and one is to have smart algorithms. And we heard already one of those algorithms this morning. That was the explanation of partial order reduction. And the aim of partial order reduction is really to reduce the size of this graph by only looking at some representative interleavings or traces, as it was called this morning. There are also other approaches, like in symbolic model checking, you would represent a set of states by binary decision diagrams. And this is a very concise representation using propositional logic. Other approaches use symmetry reductions, abstractions, etc. And so these are nice algorithms. They are quite general. And they can save you, they can give you exponential gains. So sometimes the state space becomes exponentially smaller, for instance, in the number of processes. On the other hand, there's the approach using more computer power. So say parallel algorithms. Now you can think of clusters of computers, which is a distributed memory setup, and the computers communicate over a network. Or you can think of multi-core processors. Maybe you have a large shared memory, and then you have many processors running on this single computer. And yeah, you can try to speed up your program. And there are also more modern architectures like GPUs or FPGAs or whatnot. Now, the speed up that you can get from parallelism is kind of linear at best. So if you have twice as many processors, then maybe you halve the speed, and then still you have to do a good job because often there's also some overhead in parallelization. So yeah, so on the top there are the smart things, the algorithms, which give you exponential gains, and at the bottom you only have a linear speed up. So why bother? Well, I think it's still important because even if it's only a linear speed up, well, if you use, for instance, 4,000 processors, well, your verification job goes down from a day to a second or so, or from an hour to a second. So these speedups do actually matter. But my main point is that parallelization only makes sense if you are able to parallelize these smart algorithms, because actually the basic algorithms of model checking are very easy to parallelize. But if you parallelize the basic version and you do not do the smart things, then you're losing anyway because the state space is so big. So the real challenge is here to get a parallel version that is compatible with partial order reduction and that can handle symbolic model checking, etc. And I will focus this talk on the other challenge, that we want an efficient parallel algorithm. So often there is an efficient version like linear time, and there are also less efficient versions like quadratic algorithms. Maybe it's easy to parallelize the quadratic algorithm, but here we are interested in have a parallel version for the most efficient, so the time optimal algorithm, and still show linear speedups. So that's quite tough. So yeah, what are the opportunities and why is it so tough? Well, I mentioned already shortly, there is this world of distributed model checking where you have a lot of memory because every computer has its memory and you aggregate all these memories. So now we can really store a large state space. But then of course the price is that you have to communicate between these computers. So every piece of information that you want to exchange is a message on the network, which could slow down the computation. So the limitation here is really the latency and the throughput of this network. And then if you want to achieve speedups on such a setup, then you have to redesign your algorithms. For instance, you probably need some load balancing. You probably want to hide the latency, so you make your algorithms more asynchronous. And you might even start doing speculative computations because you don't want to wait. So you compute something which you may need or may not need, just in case you will need it. So I think most of the work on model checking started in this distributed world. At least our work started in distributed, but later we moved to multi-core model checking. In the multi-core model checking, you assume that the state space is available in shared memory. So it's just the graph is in main memory and all the processes can just read this graph, so can read the state space. So the communication is rather efficient then. But still there is a limitation because all these processes tend to address main memory at the same time and the memory bus is still limited. And then there are all these things like local caches that have to be kept coherent. And also to get a correct implementation, you have to protect yourself against race conditions. So you start maybe using locks, and which are also a threat on speed up, of course, because if you have a lock, then you also are probably going to wait instead of doing useful work. And then I think model checking provides one of the hardest problems to do in parallel, because typically what we have is large hash tables. Also, binary decision diagrams rely on hash tables. And in hash tables, you have a quite irregular access pattern to the memory. So this means that, well, you access a location, then the next access to memory is a completely different location. So the local caching doesn't help you a lot. And then if you start looking into the details, if you have many processors, like a machine with 64 processors, then typically it's not a symmetric multiprocessor machine anymore, but it gets some kind of a non-uniform architecture. And we are actually quite close now to the distributed memory model, except that you don't see it as a programmer. And then to do everything efficient, we try to program in a lock-free style using compare and swap operations, be aware about memory barriers, and be aware about the cache line. So you see this kind of software becomes very hard to construct and also actually hard to get correct. Anyway, when we are at this level, it's also a little bit of engineering, and we don't have a very good complexity analysis of the parallel algorithm anymore. So in these cases, both here and here, experiments are quite important, I would say, to measure that we actually achieve some speedups and not only have parallel algorithm on paper, but also get some speedups. So this is just to sketch a little bit the area and the obstacles and the challenges that we faced when developing this research and evaluating it with practical experiments. So there's some history here I'd like to share. So actually quite early, already in the 90s when model checking was invented, there were also approaches already on parallel model checking. And one of the earliest in symbolic model checking is this work in 1990 by Kimura and Clark on a parallel algorithm to construct binary decision diagrams. And also explicit state model checking was parallelized quite early by Stern and Dill in 97. There was this parallel Murphy verifier, which worked on a network of workstations. And then there was this workshop series, this PDMC workshop series, parallel and distributed model checking. And there was a lot of work early 2000s in the realm of distributed model checking. So you see distributed symbolic model checking, distributed LTL, distributed versions of UPAL with time. We came in with distributed versions to do model checking of process algebras. There was work by Jaco and Chung about symbolic reachability for Petri nets. So I would say early 2000s, there was a focus on this distributed approach. But then in the second half of this decade, people started looking at multicore. So in Brno, there was this multicore LTL model checker. Spin became multicore in this area. There was actually also swarmed verification of spin, which is then distributed again. And then Jaco had a talk in 2009, which was one of the latest PDMC workshops, where he claimed that parallel symbolic reachability is actually very difficult. So they tried quite hard, and they had some algorithms and implementations, but it was very hard to reach efficient speedups. And that was about the time that my PhD students started working on this challenge to have scalable and efficient multicore model checking. And actually, Alfons Laarman's thesis is mostly devoted to multicore nested DFS, which is the basic algorithm for LTL model checking, like in Spin. And so nested DFS is optimal. It's a linear time algorithm, and he managed to achieve quite nice speedups in practice, which were also compatible with partial order reduction. So this was, I would say, a success in this line of work. Then Tom van Dijk was my next PhD student, and he looked into BDD algorithms, and he came up with scalable multi-core implementations for BDD algorithms, which can then be used for symbolic model checking. And finally, Vincent Blumen provided a multi-core algorithm for detecting strongly connected components, which are also very useful for model checking. And there are several attempts to this, but they are mostly based on breadth first search. But Vincent showed that you can also use, you can also have a parallel version of DFS. So a few more details. For the implementation work, what was also very important is to have a log-free hash table, which compresses the states in a nice way. And Alfons Laarman also designed such a hash table. It's quite specific for model checking in that we only add states to the hash table. We never remove states, and that's why we could make it faster and have a nice speedup. And this is actually recently redesigned. As I mentioned, he designed this parallel NDFS. Actually, this is a quite tricky algorithm. We had several variants and several counterexamples. And I'm quite happy to say that we have formally verified this parallel NDFS now in a program verifier that was done by Wietse Ortwijn. So we have a formal proof that our parallel NDFS algorithm, not the implementation, but the algorithm is correct. And this work is compatible with partial order reduction, which is nice because that was our goal to be compatible with all the smart algorithms. Now this work by Tom van Dijk, so he had he started with this hash table, but in binary decision diagrams, you also have to remove nodes that you are not using anymore. So there is a garbage collection going on. So he extended the hash table with garbage collection, and then he added caches, and he had to design a task scheduler. So there is some work on making concurrent data structures, and I will not go into the details today. But then based on that, he could implement BDDs, and then we can do symbolic reachability, symbolic bisimulation minimization, and even the saturation strategy which was so successful for Patronets, can now be done in a parallel way. And Wietse Oortwijn also made a heterogeneous version of this, which works partly on a distributed system, but within one computer node, it uses multi-core. So there's even a heterogeneous version of this decision diagram library. And then the third one I mentioned, Vincent Blume. Well, what's in this partial strongly connected components? This is actually where most of the talk will be focused on, so I will explain this in detail later. But this, again, is based on depth-first search, which is actually hard to parallelize. The distinctive feature of this approach by Vincent is to share even partial strongly connected components. We will see why we do that in a minute. And then the data structure he needed was a union find forest. So he also had to design this concurrent union find structure where you can iterate the elements. And we will see that later. But if you have this, then you can detect strongly connected components, which you can then use also again in model checking. And now we can do model checking in the usual way with Büchi automata, but this also allows model checking using more fancy automata like Rebben automata, etc. So actually, the main part of the talk has two parts. I will explain this approach to strongly connected components in a parallel algorithm for strongly connected components in quite some detail. That's the second part of the talk. And then I will show some of the extensions, like how we do LTL model checking with this, and how the symbolic tool works, and how our model checking tool is designed. And this part 3 here will be more an overview part. So part 2 is a more detailed part. Well, I will show the details. And part 3 is more an overview part. Okay. So let's start with these strongly connected components. So the setting is a finite graph, which could be the state space, and it's a directed graph, and these could be the transitions of your system. Now, what's an SCC? Well, it's actually a maximal component in this equivalence relation: forward reachability intersected backward reachability. But what it means is simply here we have the strongly connected components of this graph. So A can reach B, but B can also reach A if you go this way through E. So A and B are in the same equivalence class according to reachability, forward and backward reachability. And these are the maximal components because D can see E, but there is no way from E to go back to D. So they are in a different class. So this is of course quite well known, the strongly connected components, but it's actually quite useful for model checking. So it can be used for LTL model checking, but also for fairness, but also in probabilistic model checking, these components play a big role. For instance, if you are in this, if you have a random execution, yeah, well, you might stay in this component for a while, but with high probability, you will leave this component either to E or to J. And then you can stay here for a while, but with a high probability, again, you would leave this. So with probability 1, you would eventually end up in C, which is the terminal strongly connected component. So I just want to say that these SCCs are used in verification in several places. We use them in LTL model checking, but they are also used in other applications of model checking and in other systems. Okay. Now there's a basic algorithm for parallel detection of strongly connected components, and it's quite instructive to see it. It's rather easy, but it also has some drawbacks. But let's first try to understand it. So I will call this the FB algorithm. FB means just forward backward, and it consists of a couple of steps. In step 1, we would just select a node, a pivot node, and here we have selected E. And now in step 2, we would compute the forward closure of E. So we just follow the arrows and mark every node that can be reached from E. And we call this blue part the forward slice. Now in step 3, we compute the backward slice. So now we go backward over the arrows and mark everything that we can find backward yellow. So now we have computed the backward slice. which is this yellow part. And then in the final step, in step 4, we take the intersection of the forward slice. That's all the states that are reachable from this pivot state E. And the backward slice, that's all the states that can reach E. And of course, their intersection forms the SCC of E. So that's a nice thing. We have found the SCC that E belongs to. But there's another property, and that's that the other parts, the blue part and the yellow part, can be treated separately. So every SCC is either here, green, or it is completely in blue, or it is completely in yellow. And that means we can use parallelization, because one processor could now work on the blue part, and another processor could work on the yellow part. So this is a nice property of this FB, that you have these independent parts of the graph, which you can handle in parallel. Okay, so this is quite nice and quite easy. But the main problem here is that for every pivot node, you do a reachability. And if you are lucky, you only cut off a small part, like the SCC of E could be quite small. So you will have n of these steps. And so you will do n times the reachability. So at least in this naive version, you will do a quadratic amount of work. To be honest, there are also improvements of this using some dovetailing, which makes it n log n again. But yeah, in the naive version, it's quadratic, so that's not so nice. Because there are linear time. Of course, Tarian's well-known algorithm is linear time, and also Dijkstra's algorithm for SCCs is linear time. So let's look at those. So there's this complexity consideration. There's actually a second consideration, and that's that we would like to do the model checking on the fly. And this FB algorithm is not really on the fly, because you have to compute the predecessors. So you need to know the whole graph in order to compute this backward and forward closure. So it's not really on the fly. Now, how would an on-the-fly algorithm for SCCs look like? Well, typically we are given an initial state, and then the model checker would say, well, you can ask for the successors of this initial state, and that's it. You can say generate the state space on the fly, and you don't have the whole thing, you have to generate it. So typically we have just a next state function to the model. So let's try this. So assume we get an initial state D, we can ask for the successors. So let's do that. And then we decide to go to this successor E, and we can ask for the successors of E. So here we have two successors of E. And we follow this path. Now we have a choice again. So let's choose this one. We go to F and ask its successors. And we repeat that. We are in G, we ask for the successors. And we are in K, we ask for the successors. There's only one successor, and it happens to be F. Now, because we work in this depth-first fashion, we could save the path on the stack, and we could detect here that we actually have a loop. So we can detect that we visit the state that is on the stack. Now we know that these three states are at least in the same component. So we have detected the loop, and we can kind of glue these states together and say this is in the same SCC. Of course, it doesn't have to be a maximal SCC, because there are still some open successors. This one has not been explored yet, and this one has not been explored yet. So its successors could belong to the same state. So maybe this has to be larger, but at least these three belong together. And such a kind of algorithm is called a path-based SCC algorithm. And I'll show you in some more detail now this algorithm by Tayan. Sorry, this algorithm by Dijkstra. I will show the algorithm by Dijkstra. But let's make a sidestep. I'm drawing here a set of states. So how do we represent sets of states? And for this, we are going to use a union-find structure. And you probably remember that the union-find structure is well studied by, for instance, there is this paper by Tayan and Van Leeuwen, who studied the complexity of union find operations. And the idea is that we want to store a set of subsets, so disjoint subsets, so basically a partition of the state. So here we have one subset consisting of E, F, and G. Here we have a subset consisting of A, B, C, and D. And the way it works is that every state has a parent state. And if you follow these parent states, you get to the root of the union find part here. And the root state basically points to itself. So in this way, every node has a parent. And if you are your own parent, then you are the root. And this is the representative, E is the representative of this set EFG. And in the same way, A is the representative of this part here. Now there are these two basic functions, union and find. So for instance, if we say, what is the find of D? It basically means we want to find the representative of D. So we just follow the parents. And then here we see, we have the root. So A is the find of D. We have found the representative of D. And the other thing is to take a union. So we can also take union of such subsets. So if we want to unite F and D, what we would do is we would find the representative of F, which is E. We would find the representative of D, which is A. And then we can either let A point to E, or we can let E point to A. So now in order to take the union, we take a step from E to A. So now with one, so we have computed the representatives, and then with one pointer assignment, we have taken the union of these two things. So now the representative of F is A. So F and D are now equal after taking this union. Okay, so this is the underlying data structure to manage disjoint subsets. So now we can indeed look at Dijkstra's algorithm, which he published in 1976. And the algorithm uses a stack R, because it's path-based, so we remember the path on the stack. And but we also have this disjoint set S, which is basically a union find structure. And we also need some other sets like visited and explored. And it's a recursive procedure. So let's say we are at node V, we call SCC of V. What we will do is we will mark V as visited. So here I will add it to the visited set. And we push V on the stack. So here we have the stack, and we push V at the bottom of the stack. Or at the top of the stack, if you wish. And then we look at all the successors of V. So we look at all successors W, which are successors or next states after V. And there are three cases basically. So one case is that W is already fully explored. And this means we have visited W before and we have already taken care of it. And we can just backtrack. We just continue to the next successor. So we don't do anything here because we are already done with W. The second case is that this W has never been visited. So we have never seen W. So it's a new state. We have never seen it before. And because we are depth first, we will now first handle this W. So we do a recursive call to this W. That's the second case. And the third case is all the other stuff. So in the third case, we have a state that we have seen before, but it's not yet completed. But then it must be on the stack. So then this picture applies. So the successor W must be on the stack. So actually we found a cycle here because there is a path down from W to V and there is a cycle back. So we have found a cycle. What will we do? Well, we pop all this part from the stack until we get at this W. So while V and W are not yet equal, well, we take the union of the two parts of the stack. So we pop them one by one and take unions until we get to W. So after doing this, we check if V is still on the stack. So in this example, it's not because we popped all of this, but maybe when we backtrack from W, it might still be on the stack. And if it's on the stack, so if the V that we are handling here is still on the stack, then we have found a complete SCC. So we can report it and we can extend this explored set with S. And then we pop R from the stack. we pop from the stack. Here we pushed, and here we pop from the stack. Okay, so that's in a nutshell Dijkstra's algorithm. And yeah, a little bit more well-known is Tajam's algorithm. I will not treat it here. But the nice thing about all these path-based algorithms is that they are linear time in the number of nodes and edges. They work on the fly because you can just explore successors and well, for every new successor, you do some work. And the drawback is that there are depth first search, which is hard to parallelize. So it's a drawback for us. And then the other class of algorithms, the forward-backwards algorithms, well, in the worst case, at least the naive version, is quadratic. You can bring this down to log n. Another drawback is that it requires predecessors, so it's less on the fly. In order to know all the predecessors, you have to compute the whole state space. But the advantage is that this is based on breadth-first search, or at least the reachability can be done in breadth-first search, so it can be done. It can be done in parallel much easier. Now there are several variants, so maybe our early graders are maybe taught this double DFS method, where you do one DFS, transpose the graph, and do another DFS. Well, it's also based on DFS, it's linear time. Dijkstra had some predecessors which were not implemented in linear time, but it's just a variant of Purdom's and Monroe's algorithm. And then in this FB school, there are also some extensions. Yeah, so I think, and this situation happened in many in much of our research, that we have an algorithm that is easy to parallelize, but it's not as efficient. So in the end, you would lose on very large graphs, because the graph, you should imagine the graph has millions of nodes, and the number of processors is not that high, maybe 100 or maybe 1,000 processors. But the number of processes is much lower than the number of nodes in the graph or states in the state space. So you really prefer the efficient algorithm, and you want to have a parallel version of this. Well, there are some things going on. So Arrive showed that the depth first ordering cannot be computed in parallel. So there's this p completeness result. So the depth first post order, computing that is p complete, and that means that it cannot be parallelized in the limit. So it seems that we cannot really get an efficient algorithm in theory. Well, I think so of course that makes it harder for us, but I think these kind of this complexity in the limit result does not really affect us, because we don't have that many processors. And then on the other hand, reachability, for instance, even shortest paths can be done in logarithmic time on a polynomial number of processors. So this is perfectly parallelizable. And this is based on results about matrix multiplication. So there is there are some theoretical reasons why DFS is harder to parallelize than BFS, or than just reachability. But still, we want to stick to this side because of this nice complexity. Now, I will show you some inspiration from an earlier paper that we had. So I'm talking about SCCs, but we took some inspiration from this world of nested DFS algorithms. So here I will only explain it by this picture. So here's an NDFS algorithm working. It has a blue search and then a red search, and we try to find this kind of cycles. And this works very efficiently with one processor, so in the sequential version. This is also the basis of spin. Now an easy way to do this in parallel is to just have many workers that independently do their own DFS. So this is worker 1, it will do a DFS. Worker 2 will do a different DFS with a different order of successors. So we randomize the search basically, but it will keep its own stack, and it will do its own work, and it will not share information. So at this point, the workers do not share information. And that's why it's trivially correct. Because, yeah, well, if one work is correct, we just duplicate the work, so it's still correct. So why is this useful? Well, it's actually useful in the case there are bugs, because if there's a bug in the system, then with 3 workers, you are probably finding the bug earlier than with 1 worker. So there is some speed up here for bug finding. but there is no speed up for full verification because all the workers would have to do the whole state space. So this is the starting point, and then we try to improve on this by avoiding duplicate work. So now we start sharing some information. For instance, you could share the information of the red states. And if the second worker sees a state that is already read by the first worker, then it will backtrack and do its own work. So we try to share some information. And by sharing information, we avoid duplicate work, right? I hope this is clear. So instead of every worker going over the whole state space, this worker goes over part of the state space because it sees, worker A1 did this work, so I don't have to do it anymore. Now, this is very, very tricky because if you do this, you lose the depth first search property because every worker here has a random path down. And the depth first of worker 1 is different from the depth first of worker 2. So the question is why this would give a correct algorithm. And this appeared to be very tricky. And basically there were two strategies, and they were both published in the same conference in ADVA by two different teams. So this is Alfons Laman and me. We had a publication in this ADVA, but also Evika Lista and Laura Petrucci had a paper in the same conference addressing the same problem, but with a different strategy. And their strategy was to share a lot of information, and then the algorithm would not be correct. So they would detect it, and then they would repair violations of the DFS work. And the repair procedure is sequential. So they share a lot of information, avoiding duplicate work, but the penalty is that they have a sequential repair procedure. What we did is we share less information. We actually only share the red state and not the blue states. So we share less, which means that we have a little more duplicate work. But then we could prove that we never violate the DFS order. And our price was that at some points we needed some locking between workers. So it's kind of a coincidence that these two things appeared at the same conference. And in the next ADVA in 2012, we actually presented a combined approach that had the advantage of both things. Well, this is an aside. So let's go back now to SCCs, and let's try the same strategy for SCCs. So consider this is the initial state of the state space, and we have here a blue worker that decides to go to the left, and a red worker that decides to go to the right. So this is kind of the random DFS thing. So we do DFS this side, this could be Dijkstra's algorithm, and the other one goes this side and applies Dijkstra's algorithm, and they happily find some SCCs in parallel. So what could go wrong? Well, it could go wrong, of course, if the red worker and the blue worker would end up in the same SCC. And then, what happens then? And again, here there are several strategies. So in TACAS 2014, Lowe had this strategy. If two workers detect that they work in the same SCC, then one worker will suspend and only one worker continues. So it's a kind of sequential repair procedure. So every SCC has to be handled by one worker. So Etienne Renaud had another approach in TACAS 2015, but basically it has the same property. He would only communicate an SCC to the other workers if the SCC has been completely traversed. So only complete SCCs would be shared. And now and I think the advantage of the work by Vincent Bloemen, my PhD student, was that he was able to also share partial SCCs, which can speed up the process quite dramatically. So let's look why this is. So here we see a graph with small SCCs. Now here there's a lot of possibilities for parallel work. So the penalty of Lowe and Etienne Renaud does not really apply in this case because there's so much parallelism going on. But what if this is the state space with a few extra edges? We have a state space here now with a very large SCC. And now if you have an algorithm in which one worker has to traverse a whole SCC, then there is no performance gain in this thing, because one of the workers has to do all the green part. And well, it doesn't matter how many processes you have, but yeah, there's no speed up. And this can also be seen in experimentally. So here we would have here we have the number of workers, and here we draw the speed up compared to a sequential Tarjan. So here the green line is Tarjan, it's a sequential one, so it cannot use so many workers. So this is the baseline. And now this is what happened with Renault's algorithm. If we have small SCCs, we have a very nice scalability for speed up. But if there is a very large SCC, no matter how many workers we use, well, we have no speed up, or we even pay an overhead. This is just one concrete model checking example, but on this example, the algorithm by Vincent Blumen, which I will explain in detail, well, it has the same nice speed up on small SCCs, but we see it still has a considerable speed up if there is a large SCC. So here we profit from the fact that we can share partial information about the SCC, and we can still get parallel speed up. So how does this then work? I will explain it by example. So assume this is the input graph, and we would like to find the SCCs of this graph. And again, we assume that we have two workers. This would also work with multiple workers, but we do it with two here. And we have a blue worker that starts visiting from A, the initial state. It visits B, and then C, and then D. And then it sees A, and well, it has started in A, so it knows this part should be contracted, or we take the union of this part in our unified structure. So assume that worker 2, the red worker, has also started. It starts also at the initial state A. It happened to go to E. It visits F. It sees E, and it knows I was there, so I can contract this. So we take another union in the unified forest. Now worker 2 continues, and it goes to C. And now actually, we need to find a way to know that actually the C is in the same component as A, where the red worker started. So actually we have found a cycle. And based on this step from F to C, we can in principle close the cycle and take the union of everything here. But the question is, how does the red worker know this? How do we know, if we see the C, how do we know that we are in the same component as the A where we started? And for this, we extended the unified structure. So basically what we do, we have this old unified structure. So here we have A, B, C, here we have D, E, F. But now at the root of these, at the root nodes in this structure, we maintain a bit set, setting the bits of the workers that have worked on this component. So here we set the bit for the blue worker, here we set the bit for the red worker. So we extend basically the nodes of the unified forest with this bit set, which is basically a long word. And when we take the union of two of these subsets, we will also take the OR of these bit sets. So we will also take the union of the workers. So when we unite these two subsets, well, we go from D to A. Now in the new root A, we will take the union of the old bit sets. So now in one go, we know that we have this whole component, and that the blue and the red worker have been working on this component. So this information is shared in a very efficient way, basically in constant time, because, well, we had the finds, of course, but then by setting this pointer and taking the union of these two words, we have here the information that blue and red were working in this component. So back to the example, we were in this situation where we had A, B, C, D. This was already combined. We know that two workers are working on this part because blue and red started at A, and blue went to B and C. But every time we do the unions, we take also the unions of these sets. So we end up with the set BR. And now if F sees C, if the red worker sees this link from F to C, the red worker would would do the find for C, so it will find this B, and then it will see, but I was already working in this component. So now it finds this bit here, and it knows that it can unite these two. So it will take the union. And now here we take again the union of R and RB, but it's still RB. So we solved this part, how we know that if we find a state that is united with a state that is on our stack, we will detect it very quickly. So there's now one thing left, and that's how do we know that the SCC is complete? And basically, we have to track all the states that are completely explored. So assume that from C we still have successors, and from F we still have successors. Then this is not yet a complete SCC. At least we cannot know it. We only know that this is a complete SCC if we have fully explored these outgoing arrows. So now we need a way to store these pending states in an efficient way, which should be compatible with the union find procedure, and which also should be such that we can distribute the remaining work. We do not want that one worker has to take care of all these states, because then we lose parallel performance. And for this, Vincent came up with a cyclic list. So what we will do is we will put all the states that we still have to do in this cyclic list. So a state is busy if it still has to be taken care of. It's an open state, not completely explored. And a state will be done if it's completely explored. So the done states are completely explored. And this has a nice property because, well, the busy states from a cycle, so maybe the workers can work on this in a parallel way. So maybe worker 1 is looking here, worker 2 may be looking here, and worker 1 just follows the list, and worker 2 follows the list. So they can kind of work in a parallel way, getting rid of all these busy states. And if a worker is behind, it could look at an old one. So maybe worker 3 is very slow, and it wakes up only after 3 years, and it is in this old state, which is not busy, but now it can just follow this structure and get back to the busy states. So that's in a nutshell why we have this cyclic list. I have to clear this. Okay, so yeah, what about maintaining the list? Well, now we have a little bit complicated structure. We have the union find structure, which are the dotted lines here, but we also have the cyclic lists, which are the blue lines. And remember, we also have here this word of the workers, which I do not show here. Now, if we have two of these subsets, it's quite easy to join them. If you want to take the union of these two, well, first you do the union in the union find structure, which is just redirect this route to this route, at this thing. But if we have these two cycles, it's also easy to merge them into one cycle. So you just you can merge these two cycles by these two assignments to blue here. And now we have one thing in the union find forest, but also linked with one big cycle. So we can easily do the merge still by these two pointer operations. And how do we remove elements? Well, I mentioned already, we do not really remove an element, we just jump over it. So if we have this cycle and we want to remove this element, we would just rewrite this blue edge, get a smaller cycle, but we keep the old one because there might still be a worker that is looking at this thing. And that old worker can now move forward to get back on the cycle. And well, these are the ingredients. Now I can show you the pseudocode, but it's now very similar to Dijkstra's algorithm. So what we do is we have now it's a parallel algorithm. So I show you here the code.
So, Jaco, a question?
Yes, sure.
So maybe I missed that, but in which scenario do we need to remove elements in the model checking?
So it's here. So we have these states to explore. So if we have fully explored this state, we can remove this from the to-do list. So you should see this as a to-do list, the list of the states that you still have to do. Mm-hmm. So if we generate the states from C, then C is not yet fully explored, because it might still have successors that belong to the same state space. So we get two new states to the explored list, but if we have closed this, then these two are done, and then if the successors of C are done, then C is also done.
Okay, so the to-do list is like the marking array, or?
So the to-do list is the cyclic list. So basically, this is the to-do list. These are the states that we still have to do. So a worker can just pick a state from this and handle it. And if it's done, then this is deleted. Well, it's not really deleted, but it's removed from this cyclic list in the kernel here. So all these states that point to this are done, and we keep a cyclic list of the to-do list. Yeah. Maybe it's more clear in the algorithm. If it's not clear after the algorithm, then we can go back to the question maybe.
Sure.
So here we have the code for worker P. So P is just one of the workers. It looks very much like Dijkstra's algorithm. So union find SCC also works with the state V. And when we enter V, the first thing we do is we claim that we as worker P are working on V. So what we do is we add this bit to the union find forest. You remember in the root of the union find forest, we would set this bit. And this is also the place where we start putting this V to the cyclic list. So here's where the cyclic list grows. We are going to work on a new V. It's not yet fully explored. So we add this now to the cyclic list. And then we proceed like Dijkstra. We push a V on the stack. Now the stack is local to worker P. So every worker has just its own stack. So the stacks are not shared. So we push V to the local stack of process P, RP. And then, now we still have to do, normally we would go to the successors of V, but now here is again where this list comes in. So we have a list of things to do regarding V. And what we do is we pick from this list. So we have this cyclic list, and this is the work that we now have to do. And we pick elements from this list until the list is empty. So while we can pick an element from this cyclic list, V prime, we continue with this V prime and we do the work that we need to do. So this V prime is basically, these are all the states that are equivalent to V, because they are in the same cyclic list, which means they are also in the same set in the union set forest. So this is where we need to traverse this union find structure or this subset, and that's where we use the list. We can enumerate them.
Okay, so Jaco, we're running close to another 5 minutes. Would you be able to wrap up?
Yeah. I will close this part in 5 minutes. Sure. Yeah. So what do? So we have some state that we have to do some work on. We take a random successor of it, and we randomize this in order to direct the workers to different parts of the state space. And then we again have the 3 cases like we had before. If it's fully explored, then we are done. We continue. If we have not seen it, which means that our bit is not in this bit set, then we do a recursive call because we still are depth first. And otherwise, it's on our stack. So we pop elements from the stack and take unions. And so this is as Dijkstra dictated. And then we are done with P prime, so we remove it from this list, from the cyclic list. And this remove was this shortcutting. And again, if we are still on the top of the stack, then we have found a complete SCC and we can pop it. And in this place, we also make this state dead, because here we are fully explored, so we can make it dead. Okay, I have to speed up a bit. So this is not completely linear time. It's if you think about the worst case, and by the way, this is not a formal analysis, but the worst case, it's kind of linear time times this inverse Ackermann thing that comes with union finds. And as I said, it's not completely formal, because if you do a correct union find, you also have to do the union in the proper direction. You have to point the small set to the large set. We didn't do that. And then also in the worst case, all the workers in lockstep follow the same path. So yeah, it's times the number of workers, because every worker does the same amount of work. But this is very unlikely in practice. So in practice, because the workers go to a different part of the state space, you will get this speed up by a factor P. So that's what we observe in experiments. And I will quickly show. The last remark on this is that actually we refer a lot to Tarian, but now Tarian also referred to us, because in 2019 they improved this concurrent set, this concurrent union find structure, and they also get some low bounds or upper bounds on the speed up. So that's nice. Yeah, here are some figures. So here's a case where both Renault and our work speeds up because there are small SCCs. Here's this case where we still have speed up because there are also large SCCs where we speed up, but Renault could not handle this case efficiently. And there's also a case where where the speed up goes away at the end. So there is still room for improvement in such cases. These are all standard model checking models from a benchmark. So I will wrap up, and I think I have to skip the symbolic part because I spent my time on explaining this SCC algorithm in detail. So I will skip this symbolic part. I will show you a little bit how this can be used for LTL, and I will show you how this LTSmin model checking looks like. So for LTL, the question is not find all the SCCs. The question is there a loop with this accepting state? So that's the question that we want to ask. But we can actually use our SCC algorithm. So assume that worker 1 goes here, and then worker 2 goes here. Well, worker 1 has found now this SCC, but it's not accepting because there's no accepting state in this. But worker 2 goes here, and worker 2 finds this accepting state, but it is not on a loop, not directly on a loop. And now together, they know that there is an accepting state, accepting cycle. So this is a nice way where worker 1 and worker 2 work together. Nobody saw an accepting loop, but worker 1 saw a loop and worker 2 saw an accepting state. And together they know it's in a cycle. So this is a nice example, I think, where we have some speed up within one SCC. But this is the direct path from SCCs to LTL model checking. Yeah, I will skip this part about TGBAs, and I will skip the part about model checking, about parallel model checking. Let me just say that we have implemented all this in LTSmin, which is a model checker that is that handles many input languages. So we have process algebras, we have Promula, which is the input language of spin. We can handle timed automata, we can handle PDMC, we can handle models in Pro-B. We can handle so many models because we have this nice interface architecture. So we have standardized the next state function. So there's a language module that just generates next states. And our tools here just ask for next states through this language. And this is very fruitful because you can even have a more complicated setup. So here we have 2 instances of this state space. So we get the next states from Promula maybe. And now we have a partial order reduction block. And we ask here the next states from the reduced state space. So now we can have nice combinations of multi-core explicit state model checking with partial order reduction that still works for several languages. So this is the multi-core LTL part. It has partial order reduction. You also have the symbolic part, which now uses parallel BDDs, which I have skipped in this talk, but we have a parallel BDD library. And one can do now symbolic model checking for Promula models, or for process algebra models, or for pattern nets, etc. And we also have still a distributed backend. This is the oldest part, but it's still working. And this can do reachability and bisimulation reduction. Yeah, for the record, I have here a list of papers which you can consider if you want to study this. We have some handbook chapters on this. We have some tool papers on LTSmin. Here's a lot of papers about parallel SCC algorithms, if you are interested. Here are some papers on parallel or distributed LTL model checking, including the ones I mentioned. And here is some literature on parallel BDD algorithms, in case you are interested. So it really started in the 90s, but there's a lot of activities here recently. And with this, I'd like to stop the lecture and give some space for questions if there are any. Thank you.
Thanks. Thank you, Jaco, for that excellent talk. So are there any questions? So maybe while the others are thinking, I mean, so I had one question. So when you in this LTL model checking, do you also, so one probably needs to report a counter example.
Yeah.
And so is that easy to do in your setup?
I would say it's a little harder. So let's go back. Let's go back to this picture. It's a little bit harder now because worker 1 has this on the stack and worker 2 has this on the stack. So you would have, and we did not implement this. So you would need a procedure. I'm sure it can be done, but you would now, at the end, if you know there's a cycle, you would have to inspect the stacks of these two workers and construct one path out of these two stacks. So I'm sure it can be done, but we didn't implement it. And I would say it's a little bit harder than with NDFS because there you have the example on one stack. And for the parallel NDFS, we actually did implement it. So for the parallel NDFS, we give back counter examples. Yeah, okay. But for the SCC variant, we didn't implement that.
I see. Okay. Okay. So I had another general question about other, domains of verification where these ideas might be useful.
Yeah.
So, for example, in a like a fixed point computation in a program, like doing abstract interpretation or data flow analysis.
Yeah.
Would some of these ideas apply there? I mean, you're not exactly finding these strongly connected components, but
I think SCC strongly connected components are of course used everywhere. I guess also in analysis of programs, but I think some of these techniques are quite general. So there's this concurrent hash tables, which of course is quite generic. We built some task scheduling with very fine-grained tasks, this double-ended queue thing. So there are some of the data structures that can be reused in other analysis tools. Some of the higher level algorithms are the SCCs. I believe that this parallel DFS approach, I think could also apply to many search algorithms. So everywhere where you would prefer DFS over BFS, this could be interesting. I think BFS is the first preferred thing. So if you just need reachability, I would use BFS because it's really much easier to parallelize. But BFS gives you less guarantees. So there are some invariants of DFS that are essential in some cases, like for SCCs, like for NDFS. You need the DFS, the post-order guarantee. And in all these analyses where you need the post-order guarantee, I think you might consider this parallel DFS approach. But I don't have an approach out of the box because for all these cases, we needed to think very hard. What is the invariant that we are violating? And how can we avoid it? So can we do with a little bit less than post order? And so this was always a bit problem specific, but I'm quite sure if I would see the next problem which really needs DFS, I would be confident and try to see how we can liberate a little bit of DFS order and try to parallelize the algorithm. Yeah, so I think the strategy could be reused, I guess. Yeah.
Okay.
And then another way to go is to go to different hardware. So many researchers are now looking at GPU algorithms. I didn't do that, but many of my students also went there. I've been looking a little bit into FPGAs. So you could try to do BDDs on FPGAs, for instance. I saw some papers there. There's not much. I know some people look at model checking on quantum computers. I really don't know if this is useful or not, but the thing is that the quantum computer can do some search in parallel, and maybe it's useful for model checking. And then, of course, there is this whole world of SAT solving, and there are competitions on parallel SAT solving. But it seems that the sequential SAT solvers use very ingenious search techniques, which are very hard to mimic in parallel SAT solving. So I think currently, actually, parallel SAT solving is not solved, and the sequential ones are so smart and can sharing the information that you need for learning clauses, etc., provide so much communication overhead that this is still very hard. So there are some successful papers, but I think for SAT solving, I would consider this still as unsolved. And then my current interest is go more towards parameter synthesis and strategies and use parallel algorithms for those. So I'm now more working in this area.
Okay.
Yeah.
Right. Thanks, Jaco.
Hi, Jaco.
Yeah.
I'm Alvin, and a student at. Hi. So my question is, with the NUMA architecture, so when the number of processors increase, you said it's almost like the distributed, approaching the distributed model. So
yes.
Are you using a message passing type of communication in that case, or?
Not really. Let me find some space to draw. Oh, here I can draw. So actually, so in a NUMA you have these memory blocks, and here's a memory block, and maybe here's one, and then there's these are connected, of course, and then you have the processors. So there are a couple of processors here and here and here. Now you are right. It's a kind of distributed system because you have distributed memory. But from the programming point of view, you don't see that. So you can just say A5000, and the computer or the operating system determines where this ends up. So all the message passing is done at the lower level by the cache coherence protocol. But still, so we do not address it in our algorithms, but in our implementation, we are aware of this. So if we have to allocate some data, for instance, if you have a hash table, and then there's some data for the hash table, we will allocate these blocks close to the processors. So our allocation strategy is actually aware of this NUMA strategy, and we will let local processors do the memory allocation. So in the implementation, you really need to exploit this kind of structure in order to get experimental speedups. So I would say it's important for doing the experiments to understand such a machine, but our algorithms do not really depend on it. And we do not explicitly pass messages, but we are just aware of how the machine works.
Okay.
I hope this is kind of, it's a very much an engineering answer, but I have not studied this in a systematic manner.
Yeah, and an extension to this, did you hit any limits on the scalability of because of the memory, the total memory available in the system?
We have not perceived limits due to the machine, but we have seen a lot of limitations due to the models. So for instance, if your model is a linear model, if this would be the model, and every process starts at the initial state, then there is hardly any opportunity to speed up, because every processor has to start here. And the only thing they can do is go down. So for such models, the speed up is very limited. So we need some kind of bracing structure, because now one worker can go here and the other worker can go here. And so we have speed up in the typical case where you have interleavings of processes. But this is also a bottleneck for proving theoretical properties. So we can never prove theoretically that we achieve certain speed up because it depends on the structure of the model. They should be kind of broad and they should not be very narrow. I think that answers.
Thank you, Jaco. So what I was thinking is, if it is so close to the distributed one, can it be can it be extended to be running into systems, like into a distributed system?
I think we would need extra work. So we did that, for instance. We started with distributed systems and we also ported our BDDs to distributed systems. But then you need more asynchronous. So you cannot send all the packages one by one because the latency of the network is much higher than the latency in this network. So what you typically do is you take large frames of messages. So this is called latency hiding. Let me clear everything. Yeah. So we would, instead of sending all kinds of small messages, we would make buffers of many messages, like an MPI, and then send the buffer at once. But now your algorithm must be more asynchronous because it cannot wait on the return. So it just fires a lot of jobs. And later it gets all kinds of replies back. So I would say you change your implementation considerably if you are working on a real network because the latency is so much higher. Now you might ask, could you use this technique to speed up the NUMA version? Maybe you can, I don't know. I really don't know the answer. It could be that if you use such strategies on the NUMA, then it's still better for caches. There are these IO efficient models, we are trying this out now. We are trying IO efficient algorithms for BDDs. We get a lot of speed up if disk is involved, but we don't see a lot of speed up only between cache and main memory. So I think the latency penalty for networks and disks are really much higher than the latency that you see within a NUMA architecture. But I'm not really a hardware expert, so I only have a very vague. I have some experience, but not a very deep understanding of it.
Thank you.
Okay, are there any more questions? Okay, so looks like that's the end of it. So thanks, Jaco, for that excellent talk.
Yeah, thank you. Thank you.
So I think since we are now at the end of the workshop, I think Prakash would like to say a few words in closing.
Yeah, thanks, Deepak. Yeah, so with this, we come to the end of the workshop. Thanks to many of us. Firstly, thanks to the FST TCS organization team. They did an excellent job considering, given the extraordinary situation. We also thank all the speakers for giving excellent talks. I personally enjoyed it, and I'm sure all the audience here enjoyed it too. Finally, we thank the audience for being here and making this program a success, especially given that it's slightly odd time for many of us. Thanks a lot to everyone. And yeah, thanks again.
Thanks for organizing this. It was excellent.
Thanks.
Right, let's give Prakash and see what's on our hand also for the organization. Thank you.
Okay. Thanks, everyone. Yeah.
Okay, so Prakash will close the meeting.
Yeah, we close the meeting.